Hello everyone. So now this is the last chapter for the first semester, which is sampling distributions and the central limit theorem. And let's get started. Let's look at the chapter 7.1 introduction. In statistics, we want to do some inference about the population, and to do that, we randomly sample some amount of samples from the population, and uh, and to specify about the population, to do the inference about the population, we look at summary statistic for the population. And here comes the definition 7.1. A statistic is a function of observed random variables in a sample and known constant. And so, for example, sample mean y bar and the sample variance s square, and sometimes the minimum of the samples y1 and the maximum of the sample and the sample median and so on. They are all a statistic to describe about the population. Okay, let's move on to example 7.1. A balanced die is tossed 3 times. Let y1, y2, and y3 denote the number of spots observed on the upper face for tosses 1, 2, and 3 respectively. Suppose we are interested in y bar, the average number of spots observed in a sample of size 3. What are the mean mu y bar and the standard deviation sigma y bar of y bar? How can we find the sampling distribution of y bar? Okay, we are tossing balanced die in 3 times. So what would be a simple event? Like a simple event would be observing all ones for the 3 die. This could be a simple event. And how many possible simple events? So we have 6 events for the first die, 6 for second, 6 for the last one. So the total possible event would be 216. So the probability of a simple event, or equally likely simple event, would be 1 over 216. And what else? About the mean and standard deviation. So what we know is expected value of yi is for one die, the expected value would be 3.5. And what about variance of yi? Variance of yi. Uh, for yi 1, 2, 3, 4, 5, 6, or are equally likely. Uh, so we can get the variance, which is expected value of yi square minus expected value of yi. And actually, you can try to get this by yourself. You will going to get the variance of yi from this distribution, and from here you can derive the expected value of y bar, which is expected value of 3 over y1 plus y2 plus y3. And so this is by using the formula that we have learned in the previous chapter, you can get this as 3.5. And about the variance of y bar, variance of y bar, which is variance of 3 over y1, y2, y3, and we can have 3 variance of I and 3 over variance of yi. Yeah, if you calculated variance of yi, you can calculate the variance of y bar. And what else? Oh yeah, how can we find the sampling distribution? And so to get the sampling distribution of y bar, we can get it directly, like if we have 1, 1, and 1, then the y bar is 1, and the probability is, since there's only one event, it's 1 over 216. And what about the second case, like 1, 1, 2? There are three number of possible cases, to where to pose these two. And so in this case, y bar is 4 over 3, and in this case, we have three possible events, so it's 3 over 216. And next case is y bar can have 5 over 3. 5 over 3, we can have 1, 2, 2, or 1, 1, 3. Arranging these two events, and there are three events for here and three events for there, so we have total 6 events. Like this, and by doing this, we can get the sampling distribution. The last one is all die have value 6, which is 6, and in this case it's again 1 over 216. So this is the table that you can get. How can we find the sampling distribution of y bar, and then actually you can calculate it like this way. Okay. And actually, in the figure 7.1, we simulated sampling distribution of y bar. What it means that uh, we rolled the die about 4,000 times, and we measured the frequency of the die. How many times uh, y bar get 1? How many times y bar get 1? How many times y bar get 4 over 3, how many times y bar get 5 over 3, 6 over 3, like that. We can count the frequency and then draw the graph of the simulated sampling distribution. And here's realization. And from this sampling distribution, we can estimate the mean and standard deviation, and so on. Okay, let's move on to chapter 7.2, sampling distributions related to the normal distribution. And in many cases, we can assume that a sample is from the normal distribution. In this chapter, in chapter 7.2, we do the inference when the samples are drawn from the normal distribution. Here comes the theorem 7.1. Let y1 to yn be a random sample of size n from a normal distribution with mean mu and variance sigma square. Then the sample mean y bar is calculated like this, and the y bar is normally distributed with mean mu and variance of sigma square over n. So this is our first theorem, and actually the derivation of this, the y bar follows normal distribution. This is the first thing to prove. The second one, mean is mu, and the third one is variance is sigma square over n. They can be proved by using the theorem 6.3. In theorem 6.3, if y1 to yn be independently normal distributed with this, and the u when u is like this, u follows normal distribution with expected value of this and variance of that. And if you put if you check all the y1 to yn follows normal distribution with mu and sigma square, and then a1 to an, let a1 to an are 1 over n, 1 over n's, 1 over n, then this u could be the y bar, and so when ai are 1 over n, ai are 1 over n, this thing becomes mu, and also this thing becomes n over n square sigma square, which is sigma square over n. Okay, let's move on. Okay, let's move on to example 7.2. A bottling machine can be regulated so that it discharges an average of mu ounces per bottle. It can be observed that the amount of beer dispensed by the machine is normally distributed with sigma equals 1.0 ounce. A sample of n equals 9 filled bottles is randomly selected from the output of the machine on a given day, and here all bottled with the same machine setting, and the ounces of beer are measured for each, and the problem is to find the probability that the sample mean will be within zero point 0.3 ounce of the true mean mu for the chosen machine setting. Okay, so what we want to calculate is this: find probability of the sample mean y bar will be within zero point 0.3 ounce of the true mean mu. So y bar minus mu within zero point 0.3. So within zero point 0.3 minus 0.3 and 0.3. Okay, this is what we want to calculate. And here, what we know is y bar follows normal distribution with mean mu, and sigma square is sigma square over n. And so this is n is 9 here, so sigma square over 9. And so the standard deviation for y bar is 3 over sigma over 3. And so to make this as a standard normal distribution, we divide um, we divide and here sigma is 1, so sigma is 1, and so y bar minus mu divide by 1 over 3, which is multiplying 3, so it is 0.9, and also here minus 0.9. Okay, so and since this one now follows a standard normal distribution, and so you can calculate the probability using the table, the normal distribution table. Okay, let's move on to example 7.3. Refer to example 7.2. How many observations should be included in the sample if we wish y bar to be within zero point 0.3 ounce of mu with probability 0.95? Okay, in the previous example, we calculated the probability of this event. Um, um, when n equals 9, but this time we know the probability, but we don't know the n. And so the problem is that uh, mm, we want to calculate this probability equals 0.95, and then what sample size do we need for this? And about this, the distribution of y bar is follows normal distribution with mean mu and variance sigma square over n, and here sigma square is 1. And so to get the normal distribution, we want to have y bar minus mu divided by 1 over square root of n. It will follow normal distribution with mean 0 and variance of 1. Okay, so we will use this. And actually this is square root n times, and actually this is square root of n times this thing. So the probability of minus 0.3 times square root of n, and square root of n here, y bar minus mu is less than or equal to 0.3 square root of n equals 0.95. And about this range, actually, in the normal table, it is 1.96, 1.96 z, 1.96. This 1.96 range, the probability is 0.95. We know this. So this 0.3 times square root of n is equal to this thing. So 0.3 times square root of n equals 1.96. And you solve it for n, you will get the answer for this example 7.3. Okay. Okay, let's move on to theorem 7.2. Let y1, y2, and yn be defined in theorem 7.1, which means that each y1 to yn follows normal distribution with mean mu and sigma variance sigma square. Then zi, which is the normalized one, yi minus mu divided by sigma, are independent standardized normal random variable. And then sum of all zi square has a chi-square distribution with n degrees of freedom. Okay, so to prove this, and actually we will recall the theorem 6.4 from the previous chapter. And in theorem 6.4, let y1 to yn follows normal distribution with mu I and variance sigma I square. And then and actually if we apply theorem 6.4 in the problem of theorem 7.2, we can directly get the result that this will follow the chi-square distribution with n degrees of freedom. Uh, okay. Okay, let's try to solve theorem 7.3. Let y1 to yn be random sample from normal distribution with mean mu and variance sigma square. Then this quantity m minus 1 times s square divided by sigma square, which is this, has a chi-square distribution with the, n minus 1 degrees of freedom, and also y bar and s square are independent random variables. So what we want to prove here is that we want to prove that y bar and s square are independent, and also this thing follows chi-square distribution with n minus 1 degrees of freedom. In the textbook, it proved the simplified version of this, and the rigorous proof is solved in the exercise problem of maybe chapter 13 or something. But I'd like to give you more rigorous proof here. And brief sketch is something like this. Suppose y1 to yn is a random sample from normal distribution with mean mu and variance sigma square. And we want to firstly prove that y bar is independent of yi minus y bar. And by using this result, we were going to prove that y bar, if we have this y bar and s, and this s is function of yi, y1 minus y bar, and yn minus y bar. With this result, we can say that y bar and s square are independent, and after that we will check this this equation. And here this one follows the normal distribution, and so the square of sum follows chi-square with n degrees of freedom. This one follows chi-square with n degrees of freedom, and this one also follows normal distribution with mean 0, variance 1. So uh, this is z square. So this one follows chi-square with 1 degrees of freedom. And since s square and x bar are independent with moment generating function trick, we can prove that this one follows chi-square with n minus 1 degrees of freedom. This is the brief sketch for the theorem 7.3. Okay, let's firstly prove the first statement. Suppose y1 to yn is a random sample from a normal distribution with mean mu and variance sigma square. It follows that the sample mean y bar is independent of yi minus y bar. Okay, and for the joint density of y1 to yn, we can specify it like this. And to prove this thing, let's try this trick. Try to define new random variables u1 and ui this way. And so u1 is y bar and u2 is yi minus y bar. And also y2 minus y bar. u3 is y3 minus y bar, and un is yn minus y bar. And if you define like this, you can check that y2 is y2 is u2 plus y bar, which is u2 plus u1. Y3 is u3 plus u1, and yn is un plus u1. And also, what is y1? And y1 is ny bar minus y2 minus y3 minus yn. Okay, so this is nu1 minus y2 is u2 plus u1 minus y2 is y3 is u3 plus u1 and minus un plus u1. And so we have n number of u1s, so these cancel, and we have minus u2 minus u3 minus minus un. Okay, and so when we are calculating joint density for use f of u1, u2, and un, we calculate it for here's joint density for y's, y1 to yn, and here's Jacobian, dy1 to dyn divided by du1 to dun. And here's Jacobian. And to calculate this Jacobian, this is Jacobian, big Jacobian matrix. And for y1 is here. For y1, dy1 du1 is 0. dy1 du2 is minus 1, minus 1. And for y2, dy2 dy1 is 1, dy2 du2 is 1, and others are all 0. And for third one, dy3 du1 is 1, 0, 1, and you can check that this is the last one is like this. And if you solve this determinant, you can check that you can calculate it. It is absolute value of n. So so actually this is uh, 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 this times minus this times and these times plus this one. Actually sum of n number of ones that going to absolute value of n. So this Jacobian can be calculated as n, and let's move on in the next slide. Okay, so the joint function of joint density function of u1 to un can be written as joint density function of yi's times Jacobian, and here the Jacobian component is calculated as n, and for this we should put yi's to function of u's, and before we do that, we will re-express this one and put ui's, and so this part can be written as this, and this part also can be written as this. And why is it true? It's because sigma yi minus y bar plus y bar minus mu square, and this part can be written as this, and in here if we group these, and you can write it as sigma yi minus y bar squared plus 2 sigma yi minus y bar times y bar minus mu plus sigma y bar minus mu squared. And actually from here this is constant, so this sigma is just summing up these constant n times. So the last part is n y bar minus mu squared, just like this one. And the second part second part is 0 because this part is constant, so it can go out from the summation, and this summation of yi minus y bar, this part is actually 0. Why this is true? Because sum of yi is actually n times y bar. Because the definition of y bar is sum of yi divided by n, so sum of yi is n times y bar, and here y bar is constant. We are summing up this n times, so this is n y bar minus n y bar, and that equals to 0. So this part can be divided as a sum of this thing and that thing, and from here actually this part you can write this as yi minus y bar squared plus from you can sum I equals 2 to n of this, and from here y1 minus y bar, because sum of yi minus y bar, as I said, this is 0, equals 1 to infinity, and 1 to n. Since this is 0, you can say that from here y1 minus y bar can be written as this. So uh, so y1 minus y bar, this one is this thing, and so we can write everything with u1 to un. So y bar is u1, and yi minus y bar from I equal to 2 to n are ui's. So we can write the you can write this part with ui's, and what we can check is that this part is inside of the exponential part. So um, the function of u1 to un is constant times exponential part of n 1 over sigma square uh, of these. And actually, since this is exponential part and some of them, you can write it as product of u1 and u2 to un. So uh, this this joint density function of u1 to un can be written as h of u1 times g of u2 to un. And by the extended version of theorem 5.5, we can say that g of u1, maybe h of u1, and but it doesn't matter. Any arbitrary function for g and h, gu1 and hu2 to un are independent. In theorem 5.5, we have g of u1 and h u2. If the joint density can be written as g of u1 times h of u2, then u1 and u2 are independent. The extended version of that theorem is like this. If the joint density function can be written as this one times that one, this u1 and u2 to un, they are independent. So, okay. So far, we proved g of u1 and h of u2 to un are independent, and here u1 is y bar, and actually y1 minus y bar can be written as this, and this is a function of u2 to un. So this is function of u2 to un. And so y bar and y1 minus y bar are independent, and similarly y bar and each of yi minus y bar I equals 2 to n, you can prove they are independent, and s square is function of yi minus y bar. So s square is function of y um, 1 minus y bar, y2 minus y bar, yn minus y bar. So s square is function of yi minus y bar, and so y bar and s square are independent. Next, we know that this one follows chi-square distribution with n degrees of freedom. Why? Because yi follows normal with mean mu and variance sigma square. So this one zi follows normal with mean 0, variance 1. So zi square follows chi-square, and this is sum of n number of independent chi-square distribution, and so this is chi-square with n degrees of freedom, and we can express this by these. Actually, this is s square is n minus 1, and here sum of yi minus y bar squared. And so we put it here. We can see that this is sigma square sum of yi minus y bar squared plus sigma square and y bar minus mu. And so actually
this result is from this one, sigma yi minus mu square is some of, actually we derived it in the previous theorem, yi minus y bar plus y bar minus mu squared, and we group these, and this is summation of yi minus y bar squared plus y bar minus mu squared. And this is constant, so I equals 1 to n. So we have n number of these constant, so this is n. And so we proved this one hold, and actually this one y bar follows normal with mean mu and variance sigma square over n, and so this one follows normal distribution. So this one squared, this one follows chi-square with degrees of freedom 1, and also this y bar and s square, they are independent. So what we can see is that let p is this one, so let p is this one, and let v is this one, and let w is this one, and then and we previously we proved that v and w are independent, and from the moment generating function, if v and w are independent, we can write this way. This is moment generating function for p, and then the moment generating function can be expressed this way if v and w are independent, and the moment generating function for chi-square distribution with n degrees of freedom, it is this one, and the moment generating function for degrees of freedom 1 is this one. And so MVT is you can derive the MVT by using 1 minus 2t minus n over 2 divided by 1 minus 2t minus 1 over 2. So which is actually 1 minus 2t minus n minus 1 over 2. And this is the moment generating function for chi-square with degrees of freedom n minus 1. So we proved that V follows chi-square distribution with n minus 1 degrees of freedom. And this is end of the proof. Okay, this is the end of the lecture today, and see you next week. Thank you.